So thank you for coming to my session. I'm Masahiko Sawada, and software engineer at AWS, and I'm also a major contributor and a Postgres committer. So the title of my talk is Postgres meets Art, using Adaptive Radix Tree to speed up vacuuming. So by the way, how many of you in this room have you already used the Postgres 17 beta or development version of PostgreSQL? Good, thank you. So you might have noticed that, or you may not already, that the vacuum in Postgres 17, the vacuum got significantly faster. So this talk is related to these improvements. And I'm also going to talk about how vacuum got improved. So let's get started. In the first of my talk, I'm going to cover the basics of Radix tree and two new data structures introduced in the Postgres 17, and which are ART, Adaptive Radix Tree, and TidStore. And in the second half of my talk, I'm going to explain about the vacuum improvements. And I'm going to show some the performance improvement and performance test results. And lastly, I'm going to touch some future plans at the end. So let's get started with Radix tree. So Radix tree is a type of data structure that uses the digital representation of the keys instead of like hashing or comparing them. So it's somewhat similar to thumb index found in many alphabetically ordered dictionaries. So for example, the first character of the word can be directly used to jump to all words starting with that character. So in this diagram on the right side of this slide, the Radix tree contains 4 keys: middle, media, mount, and mouse. And each node has one or more edges to child nodes, and each edge is labeled with the prefix of the key. So you might think that we can remove some unnecessary node, especially the node with only one child, like this one. Yeah, this is a byte optimization, and there are also some optimizations that can be applied to the Radix tree, but this example is very traditional and example. It's not very performant, but it's very understandable, easy to understand. So one important property of the Radix tree is its shape depends on the key space and the length. So I mean, it doesn't depend on the key insertion order or any existing keys when inserting a new key. So therefore, there is no rebalancing operations required. And the Radix tree generally supports basic operation like insertion and searching a key and iteration, and all operations can be done in OK complexity. The where key is the length of the key. For example, in this case, the length of the key is the 5. And as shown in this diagram, the Radix tree doesn't store the entire key in its node. Instead, we can reconstruct the key from the path to the root from the leaf. So actually, the Radix tree is, I think, widely used in the many softwares. So for instance, the most famous one is Linux. The Linux is, as I understand correctly, Linux has been using a Radix tree for the pages in the management of the page cache. And also, if I remember correctly, the DuckDB also uses the Radix tree to keep the primary key or foreign key constraints. So the Adaptive Radix Tree. Adaptive Radix Tree is a variant of the Radix tree and originally proposed in the academic paper. The Adaptive Radix Tree ARTful Indexes indexing it for main memory databases in 2013, around that. And in this paper, they also proposed three key techniques: and adaptive nodes, the lazy expansion, and path compression. And actually, we have implemented the best adaptive radix tree based on this paper in the PostgreSQL. But the lazy expansion and the path compression have not been implemented yet. This is just because we couldn't have enough time to evaluate these optimizations and to see if such an optimization is worth to have, especially for our use cases. So of course, we might consider implementing these two optimizations in the future. And proposed radix tree uses the key span of 8, and which means a key span is a number of the bits of the key used in each node. So since the key span is 8, the maximum number of the child nodes a single node has is 256. And this slide illustrates what traditional radix tree and adaptive radix tree look like. And on the left side is a traditional one, and which consists of the homogeneous node with the same fanout, and all node is the same size. And it's very easy to understand, but it's also easy to see how this can be inefficient, especially when most of the child nodes are null. And on the right side, you can see this is adaptive radix tree. And as you can see, the tree consists of the homogeneous node with the different size node and the different fanout. And this is actually the key idea of adaptive node technique. So we have several types of node, and which with a different fanout and a different method for a different structure and a different method for the searching a key or inserting a key to the particular node. And we can start with a smaller node, and we can replace it with a larger node when the key is full. And conversely, when the node becomes underfilled due to key removal, it is replaced by a smaller node. And this is a key concept of the adaptive node technique. And the adaptive node technique doesn't affect key structures, but it affects only tree size and a node size. So in general, the larger span, the lower the tree height, right? From the performance standpoint, it's desirable to have a larger span in order to keep the tree lower. But if we have a larger span, that one disadvantage is the space usage can be excessive with most child pointers being null. But in ART, so with adaptive node technique, it uses the less space and has a smaller height at the same time. So which allows us to have a relatively large span. So actually it's span of 8. So the paper introduced the 4 type of node kinds: the node 4 and node 16, and node 48 and node 256. And each node has the different structure and different method. But actually, the node 4 and node 16 have almost the same structure. It has a key array and child pointer array. In node 4, we can store up to 4 keys into this node. And keys in the key array are sorted and correspond to the child pointers. So we have 4 child pointers. And node 16 is also the same, but different size of the array. We have 16 key chunks and 16 child pointers. And node 16 is when node 16 is a full and a new key is inserted, we replace it with node 48. And in node 48, instead of storing the 1 byte key chunk directly, it maintains the array of 1 byte offsets to 1 byte offset to the child pointer array. And node 256 is the largest node type, which has only the child pointers, 256 child pointers, and covering all possible keys can be represented with 1 byte, 8-bit. So the values are stored into the leaf node of the Radix tree. And the original art paper describes the 3 ways to implement the leaf nodes. That is, how to store the value in the leaf node. The single value leaves, multi-value leaves, and combined pointer value leaves. And actually, the art in the PostgreSQL uses all of them, depending on the value size and its type, like fixed length value or variable length value. So let me explain the 3 methods. The leftmost approach is a single value leaves. Here we allocate. In this example, I used node 4. So the orange box represents a leaf node. So because it's node 4, we have 4 key chunks and 4 key threads, 4 child threads. And the leftmost approach is single value leaves. And in this approach, we allocate extra leaf node to store the value. And we store the pointer to it into the slots, in the threads. And this is very generic approach, and it can support the variable length value. But it requires 1 pointer extra traversal from the leaf to the extra leaf node. So the next approach is the multi-value leaves. And in this method, values are stored directly into the slots in the node, the leaf node. So rather than using the pointers and the extra leaf nodes. So this can avoid the need for extra pointer traversal, but it requires all keys in the node, all values in the node to have the same length. It's relatively difficult to implement the variable length value with multi-value leaves. And the rightmost approach is the combined pointer value sorts. And this combines like the previous 2 methods. So if a value fits within the pointer size, typically 8 bytes in a 64-bit operating system, and no separate space, no separate extra leaf node is required. So we can store such value directly into the slots. Please.
What is the value in case of TidStore? Because it's just we are actually storing a bitmap. So what part is value and what part is the long key?
For example, I will explain about the use case of a Radix tree. But for example, in the TidStore case, the key is a block number, 4-byte block number. And the value is a bitmap representation of the offsets.
Okay.
So combined pointer value slots. So if the variable length value can fit into the pointer size, we can store it directly into the slots. But otherwise, we use like a single value leaves approach. We allocate the extra leaf and to store the value, and we point start a pointer to it into the slot.
Do you have a separate array to say which slot uses which method?
That's a very good question. And yes, we need that. So there are some implementation. The one is, for example, we can have a bitmap for the slot, indicating this slot has a pointer or value. Another approach that actually paper recommended is the pointer tagging. So we use the lowest bit, the value, to indicate this slot. Actually, this slot is actually a value or pointer. Does it make sense?
I don't think so, because the data might have the lowest bit set.
Yes, exactly. So we have, for example, in our implementation, the user can specify to use or not this or not. So let's move on to our ART implementation in PostgreSQL. So this is a development timeline. Actually, I started in 2021. I started a thread on the Postgres Hackers to improve the data tuple storage for rigid vacuum. And I started with looking for better data structures. And while the Postgres already provides the possibly good fit data structures like integer set and TID bitmap. In addition to them, I wrote some POC code. Like for example, lowering bitmap was also a candidate, and yeah, Anders Fernand proposed the Radix tree and provided his prototype patch, and we evaluate the performance of these data structures. And as a result, his prototype patch had a very, very good number, and we also discussed the Radix tree can be used in other component than vacuum in the PostgreSQL. So we decided to implement or polish his patch, and which was 2022. And the collaborating with John Naylor, we have been implementing the Radix tree in the PostgreSQL, and finally it was committed on the last March by John Naylor. So this is an overview of ART in the PostgreSQL. And in our implementation so far, we use the 64-bit key, and this is the fix. We cannot currently we cannot change that. And but the user can specify the value type, and also as I mentioned before, it's supposed the both fixed length value and variable length value. And it also supports the shared memory support, shared memory. So that means we can create a Radix tree on the DSA area. And the implementation of Radix tree, our Radix tree adopts a macro template style. Now, which means the Radix tree is defined in the header file, .h file, rather than .c file. So, and the user who want to use the Radix tree need to specify some parameters like RT prefix, RT scope, RT declare, and so on. And also RT value type is actually used to specify the value type. And then they need to include the lib/radixtree.c, and which generates the Radix tree code. The generated Radix tree is prefixed with RT in this case, and also corresponding APIs. The current Radix tree implementation provides a very simple APIs, and it has a create and free, and we can find, set, and delete a key, and iteration is also supported. Actually, the keys are returned by iteration is already sorted. And it also provides memory usage function. This returns the memory usage of the Radix tree. And this is a very simple example of how to use the Radix tree. And yeah, as you can see, the RT create function takes memory context the all radix tree is created in this memory context. And we do the RT set and RT find, and the iteration is something like that, and the delete and free. So we have the test module in SRC test module, test radix tree. So you can see more example of that there. So the value type. So as I mentioned before, it's supposed to both fixed length and a variable length value. And when you, so RT value type parameter is a mandatory parameter which is used to store the specify the value type. And if we specify only this parameter, it means the values is fixed length. Internally, we use either single value leaves approach or multiple value leaves approach, depending on the value size. And it also which is decided at the compile time. So if the specified value size is less than pointer size, for example, into 4 or into 8 or even into 64, we can use the multiple value leaves, meaning that we can store the value itself into the leaf node. And if the value is more than that, we use the single value leaves. And in addition to this parameter, if we specify the RT volume value size macro, which is, this is actually macro, it means we use the variable length values. And this macro has to return, dynamically calculates the value size and then return it. And in this case, internally, we use a single value leaves. So, I mean, we always allocate the new extra leaf node to store the value. But the most efficient way to have the variable length value is to specify the RT runtime embeddable value parameter, in addition to these two parameters. So in this case, internally we use a combined pointer value leaves approach, as I mentioned. So so in this case, the lowest bit of the value is reserved by radix tree for the pointer tagging. But we can use the combined value pointer value leaves approach. So this is the most efficient way. So one innovation in our art implementation that compared to the original art paper is decoupling node size classes from the node kinds. So node kinds means here the different node structures. We have different node structures with unique, each of which has the unique methods for finding inserting the key. And we have 4 node kinds, node 4, and 16, 48, and 256. And the idea of the decoupling node size classes from the node kind is that we have multiple size classes per node kind. So the size classes are within the same node kind have the same underlying type. So which allows us to grow or shrink the node just by using a leap alloc or just the memory copy, instead of a transfer from the old and new node, which could have different node structure. So let's move on to the TidStore part. So TidStore is also new data structure introduced in Postgres 17. And this was designed to store a large set of TID efficiently. the high-level structure of TidStore is actually very simple. It's using a Radix tree internally, and the key is a block number, which is 4 byte, and value is the bitmap offset, bitmap representation of the offset. And it internally uses the combined pointer value slot. So I mean, it uses a variable length value. And it supports also the shared TidStore, so that multiple process can share the one TidStore. And currently we support only the basic operations. It supports the set operation and is a member of operation to find, to look up the particular TID. So the high-level TidStore structure is very simple, but we implemented 2 optimization there. So as I mentioned, the value of the TidStore Radix tree is the bitmap representation of offset. So one disadvantage of using the bitmap representation is that we could waste the space if the block has the sparse offsets. So to deal with that, one optimization implemented in the TidStore is that we embedded up to 3 offsets in the header space. So a block table entry struct is actually the header of the value. And in this struct, we have bitmap, the word array, which is a fixed length one. And any words is the number of the words the words array has. And the flags is used for the pointer tagging, reserved for the pointer tagging. And between the any words field and the words field, there are 6 byte padding space in 64-bit operating system. So that means we can store up to 3 offsets there, because offset number is 2 byte. Then we have a 6 byte in a padding space. So this is the one optimization we implemented in there. So this helps reduce the Radix tree size significantly, especially when we have sparse offsets in a block. And what is better, since the header size is actually 8 bytes in total. So if we can store if the number of the offset in a block is less than 3, what we need to store is only this header, which means it fits in the pointer size. So in terms of the Radix tree, we can store the header, this header directly into the slot. So we don't need to like extra pointer traversal, so which is very good. So it can save the space as well as improve the performance. So look at performance. The second optimization is using a bump memory context for TID storage. So bump memory context is also a new memory context introduced in Postgres 17, and which is designed for a workload where the data is only inserted and never updated, and the data is freed all at once. So this perfectly matches how the lazy vacuum uses. So because during the lazy vacuum, we accumulate the TID into the store, and we free it all at once. So there is a parameter to specify whether or not we use bump memory context or not. And this is optional. By default, we use allocset memory context. So, and ultimately, we use the TidStore in the lazy vacuum But before diving into that, so let me explain what is the original motivation, some background and how lazy vacuum works in the first place. So lazy vacuum, I use the term lazy vacuum to distinguish between the vacuum and a vacuum fill. And lazy vacuum is what auto vacuum does. It's not the vacuum fill, and it can be run concurrently to the insert and the select and so on. So in the lazy vacuum, at the start of the lazy vacuum, we allocate the memory specified by the maintenance work mem, and which is for the back, we use it for the backdate items. Actually, this is how Postgres 16 works, actually. And backdate items is a key data structure for lazy vacuum, but very simple one. And as you can see on the bottom of the slide, it has items, which is flexible array, and the item pointer data is actually we call TID, which is 6 byte. And we have max items, which is not maximum number with TID we can have. And num items is the current number of the TID in the items array. So lazy vacuum has roughly 2 phases. In the first phase, we scan from the table from the beginning to the end. And we read the page and do the heap pruning, and then correct the dead TID into this struct. And we do repeat this process until either we scan all pages of a table or we reach it to the maximum number of the items. And then we move to the next phase, which is in vacuuming phase, we call it. And in this phase, we vacuum all indexes and table. And in index vacuum, we find the index tuples that differentiating to the TID in the array. For example, in the B2 index, the index tuple in the leaf node has a TID of the heap table. And we have array of the dead TID. So if that TID exists in this array, we can actually remove the index tuple. And TID arrays was the key data structure in the lazy vacuum operation, but we can see some inefficiency and limitations there. So firstly, using a plain TID array is not very space efficient because we had to use the 6 byte per TID, and we didn't any compression. And the maximum space for back dead items was limited to 1 gigabyte. So even if you specify the maintenance work mem to 6 or 7 gigabyte, it's internally capped by the 1 gigabyte. So the documentation mentioned that. And also, this memory space are allocated at once. We don't I didn't incrementally allocate the memory. And the lookup performance was also not great because lookup performance, the complexity is O log n, and where n is the number of the TIDs. So the last April, I commented the patch to use the TidStore in the lazy vacuum. This change was actually relatively simple because I just replaced the previous TID array with the TID array with the TidStore. And this TidStore uses internally the bump memory context. And then the number of tuples no longer provide any meaningful insights for users. So we changed some the column names of the pg.progress vacuum view, and we had num dead tuples and max dead tuples, but from the Postgres 17 we have dead tuple bytes and max dead tuple bytes. So let's move on to the performance test part. So I evaluated some this lazy vacuum performance on some workloads and compared it to the Postgres 16. The table I used was 3 GB or 4 GB in size, and it had 10 million rows, and with 1 bit index. And I deleted some tuples depending on the workload. I will explain that. And do the vacuum. And the maintenance work mem I used was that 1 GB to avoid the multiple index vacuum. And I measured the total execution time of the vacuum, including all phases and memory consumption. And I did the test on 3 cases, and while changing the distribution of dead tuples in the table. And I'm going to show the performance results, but please note that in Postgres 17, the mini optimization has been committed to the vacuum area. So these improvements may also contribute to the performance differences. So this is a dense case. Dense case means I loaded the insert 10 million tuples into the table, and I deleted the first 50% of the table, and making the 15 million deleted tuples in total. And the blue bar is the PG16, and the orange bar are the PG17, and the y-axis shows the total execution time of the vacuum. And I tested with both logged table and unlogged table. And I look at the performance. In Postgres 16, it took almost 10 seconds, but in 17, it took 7 or less than 5, almost 6 seconds. And also looking at memory usage, in Postgres 16, it uses 286 megabytes, whereas in Postgres 17, it uses only 70 megabytes. So this is the sparse case. I prepared the same table, but deleted the tuples, some tuples, 1 tuple on every 4 blocks. So the table has the sparse dead tuple, and in total it had 10,000 deleted tuples in total. And the trend is actually similar. And in Postgres 16, with the logged table, it took almost 15 seconds, whereas the Postgres 17, it took only almost about 6 seconds. And but looking at the memory usage, because the tuple are sparse, PG17 used more memory. In the Postgres 16, it used the almost 600 kilobytes, whereas in 17, it used 16 megabytes. So the last case I did was to use the UUID, and I created a table with 1 UUID column, and I inserted 1 million UUID data, and deleted a random 25% of total tuples, and did a vacuum. In this case, Yes, Postgres 17 had a good number. But Postgres 16, it took almost 42 or 43 seconds, whereas in 17, it took only less than 15 seconds, which is 3 times faster than PG16. And also looking at the memory usage, PG17 had a very good number. So the summary. So we can see there's some inefficiency and limitations in the previous item ID array, simple item ID array. But with TidStore, we now have a space-efficient TID storage, and thanks to the Radix tree, and which up to contribute to the up to the 20 times memory reduction. And the performance is also good. We can do the lookup in OK complexity, where k is a fairly small index in this case because it is 4. And the performance results showed that 2 times or 3 times faster than Postgres 16. And in terms of the memory management and memory allocation, the TidStore is really good because we can now incrementally allocate the memory. And that way, also, we no longer have the 1 gigabyte limit. So future plans. So during the development, we had some discussion about the other use cases of the Radix tree in the other component in PostgreSQL. So first one is using a TidStore for bitmap scan instead of a TID bitmap. So the idea is we replace the current TID bitmap with a TidStore. And another one is we use a Radix tree for the better buffer management. I'm not sure. I think Andres is more familiar with that because, yeah, I saw his presentation about maybe 10 years ago or something, and about using the Radix tree for the better buffer management. Yeah, I think if I understand correctly, the idea is we have, for example, at the end of the vacuum, we truncate the end of the table. And in order to do that, we need to validate these tables if these blocks, because these blocks are already loaded to shared buffer. But currently, we need to scan all buffers to find the buffer to invalidate. But the idea is to use a Radix tree for maybe the PAR relation, and because the Radix tree can support the range scan, so we can find the buffers to invalidate more quickly. And another a possible improvement for the Radix tree is to improve the concurrency. So actually, your current Radix tree in PostgreSQL supports the DSA, the shared one, but the locking, in terms of locking, it's not very efficient. What we do is that we have one lock per Radix tree. So we don't use like a tree lock. So we have a giant lock for each one Radix tree. And the author of the art paper also proposed a better idea in an academic paper. So maybe we can study that and implement that.
I don't think we want that type of granular locking because we have such a read-heavy workload for the buffer mapping table. The amount of locking you would do with basically lock coupling down the tree that would destroy performance completely because you would have like 5 atomic operations or something on average. I think we either want something where we get no locking for reads with like deferred freeing, or just a single lock and because we would use one radix tree per relation, it would still be like more granular than just one buffer every buffer. That's my gut feeling.
Yeah, and for collection time, you could actually build, say, 4 trees, because you have already ordered ranges. So if you have, say, 4 collectors, then just make for each range a tree, and then whatever range you are, then go to that tree. Then you can easily parallelize, and they are independent completely.
Right. Somewhat that's like, because you want to do stuff like be able to easily find the next block when writing out one block to see whether all neighboring blocks are also dirty and write them out together to reduce write implication. So you want
I mean only collection time. If you want to do the first stage in parallel.
The buffer mapping table would be for the buffer mapping table.
No, yeah, I was actually talking about vacuum.
Oh, well.
In vacuum, you already have ordered.
But there's no locking needed there.
Yeah, but the better concurrency.
Yeah, but that doesn't matter for vacuum.
Yes. Vacuum scan, that one.
But like, it doesn't, because like.
Yeah.
Yeah. Yeah, we have a parallel vacuum, but the current parallel vacuum, we don't actually need any locking, because the lead and light and the data phase is separated.
Yeah, I meant this initial byte phase, so you can basically jump it up and then do in parallel already without any congestion, because they are writing different parts of the tree always.
So another idea, so better concurrency support could be required for the buffer support or parallel vacuum scan. And yeah, I'm actually writing a POC patch for the parallel vacuum scan. And in this case, I think we need to like multiple writers and multiple workers to scan the single table. And every worker write the TID to the shared TidStore.
Yeah, but they are working on different parts of it. Because if you split it into 4, they are already ordered, and then they go to the different.
You don't know where the data is. The TIDs are very often clustered in regions, yeah. So I don't think you want to split it up.
They will be unbalanced in this.
Yeah, so I don't think that. I don't think the locking would be the big bottleneck, even if you have a single lock. I would be surprised.
No, it's so much faster anyway already that probably it doesn't matter.
So I think it's also a good idea to like separate the table to scan for each workers, and in each worker individually creates a radix, radix tree, and then merge it. I don't know.
Then I propose to actually collect into a file, which doesn't use up any memory at that time, and then you also can do some analysis before constructing whatever the lookup structure is. And that can be very easily parallelized also, so that you have just multiple files that have ordered each.
We can experiment with that. Thank you. And the last but not least, so while using TidStore in lazy vacuum improves the performance and the memory usage very much, these changes touch the very, very critical part in a PostgreSQL. The vacuum is very critical, right? And the internal data structure, the radix tree and a TidStore are new data structure. And also, there is no like on-off switch for like in terms of data structure. So if there is some bugs in radix tree or TidStore, the database is going to be corrupt in a very various way. And so, if you're interested in, so please do the more test. And we would really appreciate it if we could some feedback or bug reports actually before the official release. So yeah, there is another discussion point. So do we need something safeguard just in case? He says we can then discuss. So yeah, I'm very appreciative. I could the feedback then. Okay, that's all for my presentation. Thank you.